Hello, my name is Matthew Martin, and while this is an unconventional setup, I would first like to thank you for taking the time to look at my research from last semester in this, as I am a first-year graduate student here at the Bayer School of Natural Sciences. So my research focuses on an investigation of the redox-neutral organocatalytic Mitsunobu reaction. So a little bit of background is the Mitsunobu reaction is a organic chemistry reaction from 1967 discovered by Oyo Mitsunobu. And it's a very versatile and robust reaction that's able to convert primary and secondary alcohols stereoselectively with high yields and up to 98% enantioselectivity. selectivity. Unfortunately, due to a few limitations with the reaction, it's limited to small-scale benchtop synthesis as it requires stoichiometric amounts of diethyl azo-dicarboxylate and triphenylphosphine, both of which are toxic reagents, hazardous byproducts, and difficult to separate from the products. So, allow me to give you a better glimpse of that here. As you can see in scheme 1 as we go over the original Mitsunobu reaction. Apologies for if this is slow. It's not quite what I'm used to. But yeah, so as you can see here, we can start with the chiral secondary alcohol, and then upon using a nucleophile, we react it with one equivalent of DED and one equivalent of triphenylphosphine for the desired inverted product. Late in 2019, a organocatalytic variant of the cycle was proposed. Here, where we have a 2-HOPO core, or 2-hydroxybenzyl alcohol phosphine oxide. However, this mechanism is not without its own limitations, as there are very stringent requirements of the nucleophile, where the pronucleophile has a pK less than 3.5, excess heat as the reaction is ran at 140 degrees Celsius, and time as the reaction is ran for more than 16 hours. Here we proposed our own modified catalytic cycle, where we will use R1 in the para position of the phenol ring to denote either electron donating or electron withdrawing ligands that will help change the overall electronics of this mechanism. And our R2, which will be composed of various electron withdrawing and sterically hindering substituents. Effectively, the goal here is that by creating a catalog of various catalyst candidates that are analogous to the original design, we can explore the structure-activity relationship of the catalyst and help elucidate the roles of the catalytic cycle and the energy activation barrier that's required to run this reaction. So that ideally, through studying the modifications we make to this mechanism, we can expand the scope of reagents that are available to us. So last semester's work focused on just synthesizing new catalyst candidates, and we have begun to test those so far, along with synthesizing even more of those, where we're using R1 as electron withdrawing groups to increase the acidity of this alcohol here. As water is eliminated in this step from this phosphonium oxide, the hydrogen of the pronucleophile and the hydrogen of our phenol. So the goal is that by increasing the electronegativity of R1, we can facilitate the elimination of this water here. Furthermore, we have electron donating groups in R1 that will increase the electron density on this oxygen with the goal of stabilizing this phosphonium intermediate. So by comparing the two, we can see which is more important in measuring the activation energy for this catalytic cycle. And this will help shed some light on how we're really looking to improve this catalyst cycle and really understand the nature of the structure and activity. All right, well, that's about all that I have for you guys today. Thank you very much for tuning in.